Hi, and welcome back to AGT STEM. Today we're going to be watching a video about oxygen. So, without further ado, let's hop to it.
So comrades, welcome to lecture. What I'm going to do now, we're going to begin with an experiment to illustrate this point that the oxygen molecule, O2, has unpaired electrons.
So we're outside just to show you the reactivity of this lovely stuff here, liquid oxygen. So you can see, wonderful liquid oxygen, nice blue colour. So
Very cold.
over here on the table, we've got a tin tray, which we're going to use to contain the experiment that I'm going to show you next. So we've got our favourite liquid oxygen there, strongly oxidizing, very, very reactive. And here, I've got some cotton wool. So this is the same stuff that we use to like take makeup off perhaps our partners or our girlfriends or our wives, and it's the same stuff that we use to wipe our babies' bums.
Oxygen is an interesting element because it exists in two forms. The form which we breathe all the time is O2, two oxygen atoms joined together. And there's another form called ozone, in which has three atoms arranged like a letter V, or
Ozone is in the stratosphere and protects us from the sun's harmful UV rays.
letter V, this way up.
Oxygen has unpaired electrons within the molecular orbitals and the atomic orbitals around the structure. And these unpaired electrons give rise to colour, and that colour is blue. So blue is often perceived to be the colour of solvated or unpaired electrons, and you can see here the lovely blue colour. Now, lots of chemists are really scared when they see the blue of liquid oxygen, because liquid oxygen is very, very reactive. Generally, you only make liquid oxygen by mistake, not like today when we're making some on purpose. And if you've made it by mistake in an uncontrolled way, where there might be organic molecules, perhaps simple organic chemicals like hydrocarbons, grease, or perhaps a highly elaborate compound, then they tend to detonate and they tend to cause very energetic experiments. So, it's really fluffy, it's not very reactive, doesn't really burn, cinders, might smoulder, but here we go. We're going to pop it in the tray.
So we begin with Neil's very high-tech piece of equipment, which is a test tube on a piece of string. What we're going to do is to put some liquid nitrogen in here.
This looks like it's a fun
You can
class.
see liquid nitrogen, well, you may not see, is colorless. Okay? So this is liquid nitrogen, and what I hope you can see is that this magnet, which is a pretty good magnet, let me just show you here with my keys, that they stick pretty strongly to the magnet. The magnet has absolutely no effect at all on the liquid nitrogen. I can pull the magnet and nothing happens.
And then we're going to fill up all of the void space, so all of the space between the cotton particles with oxygen. So you might want to stand back after this bit, Brady. So here we go, here's our liquid oxygen.
Very fun.
Do you want to come in and zoom in on, see me? Okay, so here you can see the lovely blue liquid oxygen colour going into the cotton wool particles.
Let's try the same thing with liquid oxygen. So, careful of my shoes.
So here we have a match on a stick,
fun class.
and I think you can see it's probably a light. So we have our fire, we have our oxygen, and we have our fuel. Now let's see what happens if we put them all together.
The liquid oxygen. It's a very nice blue colour today. So now let's try it. Here's the magnet again, and if I take the liquid oxygen, you can see I can pull it right up here, because it's not as magnetic as my keys, but you can see there's a really big difference. It sticks to the magnet. So you can see it really is magnetic.
You ready? Okay. Woohoo! And there she blows!
It explodes. He seems way too excited about that.
Ozone is much more reactive than oxygen. So near the Earth's surface, where you and I are at the moment, ozone is really quite dangerous, because if you breathe it in, it can start reacting with any sort of molecule that has bonds between carbon. But in the upper atmosphere, ozone is extremely important because it absorbs ultraviolet light that comes from the sun and stops this ultraviolet light attacking the molecules in biological species on the surface. If it wasn't for the ozone in the upper atmosphere, all of us would be, if not dead, certainly very much less comfortable than we are at the moment.
So Neil's now connecting up a piece of tube to the oxygen cylinder, and he's going to fill up this gas jar with oxygen. And we're going to do a really classic experiment, the one that everyone learns at school, a test for oxygen, which is to relight a glowing splint. So we have a traditional gas jar full of oxygen. So here you can see we're burning a splint. Okay, so this is the wood burning in excess oxygen around us. Okay, so now what we're going to do is we're going to take the splint out so that it's just glowing. So if I blow on the splint, you can see it gets brighter. Now we're going to try and relight that splint by putting it into a very oxygen-rich atmosphere. So we'll move over to the jar and we'll put in our glowing splint. And you can see the flame comes back to life. So that's a test that everyone learns for an oxygen-rich environment.
What happened?
That's pretty cool. Just, you can have something that's like glowing ambers, put it in there and it lights right back up.
What made that happen?
Well, the increased oxygen concentration reignites and reinitiates that oxidation of the wood, or the burning of the wood. So we'll do that again. So there we go. Flame again.
Cool.
I wonder how many times you could do that, like, before it just stopped. Well, anyway. Thanks for watching. We'll see you next time. Stay smart. Bye.